Kevin Davis, editor of BioIT World, back at Exploring Next Generation Sequencing here in Providence, the CHI conference that's going on behind me. I'm joined by John Milton, Vice President of Research at Oxford Nanopore Technologies. Welcome, John.
Thank you.
You're always at these meetings, it seems, but you're never actually on the podium giving a talk. So when's that going to change?
It's going to change pretty soon. We're obviously, because of our closeness to Illumina, we have to be careful about what public statements we make. Because that could potentially affect their share price. But when we do release sequence data, we'll take it through the genome centres first, such as Sanger, in the same way as we did at Celexa.
Okay, so let me go back a little bit, or let us go back a little bit and just sort of explain that connection. And of course, speaking of Illumina, you were one of the key executives, key researchers at Celexa, the British company that Illumina bought. So why don't you just in 30 seconds or something, just take me back through sort of the highlights of your time at Celexa.
Okay, so I joined Celexa in 2001, where it was a small tech company just spun out of Cambridge University. There was about 15 of us, and I joined as the head of chemistry. We built up a big R&D centre at Chesterford, which is just south of Cambridge, made up of a large number of chemists, molecular biologists, people working on chip surfaces, enzymologists, but also engineers, optical physicists, and also informaticians, such as people as Clive Brown, who you know. And then over the next 2-3 years, we developed the sequencing chemistry that was ultimately to become part of the Genome Analyzer platform. And then we sold that in 2006, 2007 to Illumina for $650 million. And that was my exit at that point, having sort of delivered the chemistry side.
So you started off doing single molecule sequencing, and of course there are companies now like Helicos that are having some success with single molecule sequencing. I mean, I'm sure you don't have any regrets about moving away from that, which was done for important reasons going back a few years. But how do you feel actually seeing some single molecule methods actually now being commercialized and having success?
I'm actually very pleased that Helicos have managed to bring the technology to fruition. It's very, very challenging to do single molecule optical sequencing, and I always believed it was possible, but I think in the short term, to get to the marketplace quickly with something that customers wanted and that was easy to use in a sort of sensible sized instrument, I think to go to sort of clustered sequencing was a more sensible approach at the time. But I'm very pleased that Helicos have finally made it.
Just to go back to Celexa and its acquisition by Illumina, of course, Illumina genome analyzers have become key instruments at the major genome centres, the Wellcome Trust Sanger Institute, of course, the Broad Institute, Beijing Genomics Institute and others, producing the large majority of the human genome or genome sequence that's been deposited in the archives so far. Can you quantitate or put some sort of figure on the amount of sequence that is out there now in the public domain that is partly or directly you're the generator of the technology of? So
a rough estimate, and this is from conversations between myself and Clive Brown, who's our VP of Informatics, we think somewhere between 85 and 90% of all DNA sequence ever produced has been done on the Genome Analyzer. We think those are reasonably accurate numbers. Right. And I think about 90% of that has been done in the last year. So the acceleration in data output is just phenomenal.
So after the Illumina acquisition of Celexa, you took a little bit of time out and did some venture capital work and other things. And then what made you come back into the sequencing mold? You'd had such success the first time. It's hard to catch lightning in a bottle twice.
Right. So once the sort of Celexa technology was out there was no obvious next-gen technology to work on. But it was obvious that with all this sequence data that was going to be produced, somebody had to figure out what to do with that data, what did it mean medically. And so I started to look around at what were the companies that were looking to raise capital to make use of that data. Do you want to dig for gold or do you want to sell the spades? And after I've been working in the venture capital community for about 6 or 9 months, Oxford Nanopore came out of stealth mode and approached me directly to head up their chemistry and R&D efforts.
So tell us about nanopore sequencing briefly. What's a nanopore and why does it hold so much potential for DNA sequencing applications?
Okay, so nanopore sequencing is a complete step change from anything that we see currently, in that we really eliminate all the optics from the sequencing system. So eliminate the lasers, eliminate the cameras, eliminate everything to do with light, photo damage of DNA, abbreviated read length errors, etc. To be able to move to a very small system, the only real way you can do that is to move from photon-based sequencing to electron-based sequencing, so electrical readouts, things that can be miniaturized, make use of all the advances in chip manufacturing in the electronics industry, and also using the sort of nanopores that exist in nature. So the starting point, there's a lot of building blocks that nature provides, and bits of our own technology, built by humans that we can put together and really get a head start in nanopore sequencing.
So you're using a bacterial protein, alpha hemolysin protein, it's a naturally occurring nanopore. What's the advantage of that versus synthetic or artificial nanopores?
Okay, so what we actually use for the sequencing is not quite the natural version of hemolysin. We take the alpha hemolysin as the starting point. That's a reasonably well characterized protein. X-ray structures are available, but we then heavily engineer that protein to add special bits of chemistry that allow us to make accurate base calling, to attach other bits of molecular machinery to build a larger piece of molecular machinery.
So Oxford was involved, Hagen Bailey was the senior author of a paper in Nature Nanotechnology earlier this year that impressed a lot of people, a lot of observers, for showing that you could discriminate between not only the 4 naturally occurring bases of DNA but also methylated cytosines as well. Tell us just a little bit about what you did to achieve that.
Okay, so in order to do that, you need to take the natural protein, the alpha hemolysin, which looks a bit like a tube that can insert itself into lipid bilayers. We then had to engineer the insides of the barrel with an adapter molecule that could then recognize each of the 4 nucleotides and give a distinct electrical signal so that we could call the bases. I think it's important to note that so the work at Oxford University is the base calling part. That's the equivalent of perhaps the lasers and the cameras in optical sequencing. There's still a large part of machinery that has to be built onto that nanopore to give what we call an exapore, which is the full piece of sequencing hardware.
So your plan is to take DNA exonuclease and snip off individual bases one at a time, correct?
That's correct. And in fact, we can routinely build that piece of architecture now in the lab. I think that's an advance over last time we met. We can routinely attach these proteins together. We can iterate upgrades on the design in sort of 2 or 3 day turnaround period. And sort of VP of research, what I was very keen to do is really accelerate the throughput of experimental progress. So we can do about as much work in a day now as we could probably have done in 6 months previously. So there's been a huge increase in throughput. And then my counterpart, Clive Brown, has to cope with all that data, of course. And so we have a sort of a healthy competition between the two of us. Can I produce more data than he can process? Or is he saying, come on, I can process 10 times more than you're producing? So there's a healthy competition there, but obviously Clive and I have a lot of history together in working on this kind of stuff.
You should be able to work that out. Is that the long-term plan, to snip off bases one at a time? Because when nanopores were first sort of crystallized and this concept was first promulgated, there was an idea of actually moving whole DNA strands through the nanopore, right?
Right. So yes, there's these two approaches, either snipping the bases off independently or having the DNA go through like a piece of rope and calling the bases sequentially. I think it's yet to be proven which one long-term is going to be the best way of doing it, but certainly we are looking at both approaches. And shorter term, we will go for the chopping approach first.
And your nanopore system could, in principle, be used for a lot more applications beyond simply DNA sequencing.
Right, we can fine-tune the internal barrel of the nanopore, really to identify most biomolecules, with proteins, sugars, drug molecules. Essentially, any molecule that's small enough to go down the barrel, we can assign a specific signal to and tailor the nanopore to that. So beyond sequencing, diagnostics, defense applications, yes.
So just to go back to that Nature Nanotech paper where you were able to resolve the 4 bases plus the methylated bases, I mean, is there much more chemistry that you need to do, or is it now just putting the pieces together and then building the system around it?
So we now know that all our molecular machinery works. We know all the individual components are doing what they should be doing. It's really more a case of now reliable system setup, maximizing the number of wells, the number of channels, optimizing the fluidics. People become very sort of focused on the hard science, but the reality is that you have to build a product that customers can use, and it works 1,000 times out of 1,000. And it's always the little glitchy things that catch you out, bubbles in your fluidics, etc. Those problems all have to be ironed out, and that can take as much effort as the hard science itself.
And you mentioned at the beginning of our discussion a deal that Oxford has with Illumina. For people who aren't familiar with that, what are the parameters of that deal, and how is that going to help you going forward?
We don't talk too publicly about a lot of the details of that deal. I think we've made the statement about how much Illumina have invested in us.
But it's a sales and marketing, they're going to help with that side of it?
Yes, we have no plans to build our own sales and marketing force. Illumina will do that for us.
John, thanks so much for joining us. Good luck. I hope you have fun at the meeting, and we look forward to actually hearing you present here one of these days.
Thanks, Kevin.
Thanks a lot.